We now look at a few examples involving 3D vectors. Before we begin, a few reminders are in order. First, to the extent possible, we should supplement quantitative information in the figures with what we can see about vector orientation. Vector direction is from the tail to the head. We now have 8 octants in 3D instead of 4 quadrants in 2D, and we should begin by making a mental note of the signs of the components in the established coordinate system. In this first example, inspection of the figure indicates that F has positive x and y components, but a negative z component. Direction angles are defined between the vector and the positive x, y, and z axes. In this figure, theta x and theta y are both 60 degrees. Since theta z is defined between the vector and the positive z-axis, and the z component of the force is negative, theta z is an obtuse angle. This means the cosine of theta z is negative, so we should calculate the cosine of theta z from this expression. Since cosine of 60 degrees is a half, we have cosine of theta z is equal to minus the square root of 1 minus a quarter minus another quarter, which is equal to minus 1 over root 2. Taking the inverse cosine and recognizing that a direction angle has to fall in the interval between 0 and 180 degrees, we find that theta z is 135 degrees. This gives us F equals 350 newtons on a unit vector in the direction of F, which we know is cosine theta x in I plus cosine theta y in j plus cosine theta z in k, and those numbers give us F is equal to 175 newtons in I, 175 in j, and minus 247.5 newtons in k. In this second example, we want to find the resultant of two cable forces applied to the end of the I-beam. The force F1 is identical to the force we examined in example 1, so we already have its Cartesian components. We can focus our attention on F2. This problem also illustrates one of the additional complications with three-dimensional problems, in that there is a greater variety of ways of graphically showing the orientation of the force in three-dimensional space. Direction angles represent one kind of multiplanar description of a 3D vector, but other kinds of multiplanar descriptions are possible. In the case of F2, information is provided about the components of F2 parallel and perpendicular to the xy plane. Let the axis of the component in the xy plane be designated as A, and notice the right angle formed in the plane defined by Z and A. Here again we have orientation described not by angles but by rise over run, and we have a 3, 4, 5 triangle here. So even though we might calculate the angle theta, we really don't need it because we can use the definitions of sines and cosines to immediately resolve this force into components parallel and perpendicular to the xy plane. The component F2z is F2 times the sine of theta, which is 3 over 5. So F2z is 250 newtons times 3 over 5, or 150 newtons. And the component F2a is 250 newtons times the cosine of theta, which is 4 over 5. So F2a is 250 newtons times 4 over 5, or 200 newtons. Now we can resolve the force component F2a into x and y components because we have another right triangle defined here. Using the properties of sines and cosines for the right triangle defined in the xy plane, we see immediately that F2x is equal to F2A times the cosine of 30 degrees. And since we previously found F2A to be 200 newtons, this gives us 173.2 newtons. F2Y is F2A sine 30 degrees, but notice that F2Y points in the minus y direction, so we'll say F2Y equals minus F2A sine of 30 degrees, and that number turns out to be minus 100 newtons. This now gives us F2 as a vector is equal to 173.2 newtons in I minus 100 newtons in J and plus 150 newtons in K. Since we had already established previously that F1 was equal to 175 in I and 175 in J and minus 247.5 in K newtons, we can now find the resultant just by adding the individual components together. So R is equal to 175 plus 173.2 in I, 175 minus 100 in J, and minus 247.5 plus 150 in K. And that gives us for R 348.2 in I, 75 in J, and minus 97.5 newtons in K. The magnitude of R is just the square root of the sum of the squares of its components, and that turns out to be equal to 369.3 newtons. So we end up with cosine of theta x for the resultant is equal to 348.2 over 369.3 is equal to 0.943. Cosine theta y is equal to 75 over 369.3, and that number is 0.203. And finally, cosine theta z is minus 97.5 over 369.3, and that number turns out to be minus 0.264. We can then just take the arc cosines of each of these, and we end up with theta x is 19.5 degrees, theta y is 78.3 degrees, and theta z is 105.3 degrees. In example 3, we have an overhang supported by two cables. We want to know the magnitude and direction of the resultant force applied to the ring at A by the two cables, given the tension in each cable segment. Before doing any calculations, let's establish the direction of the forces at A. We'll consider cable segments from AB and AC Here we imagine a cable segment that's cut on either side with opposing faces that eventually connect to A and to B. And we'll have something similar over here for AC. So here's a segment of cable segment AC, and it has opposing faces that are eventually connected to C and also to A. If we consider a segment of cable AB, we know that it is taut, so there are forces aligned with its geometry tending to stretch it. The forces applied on the opposing surfaces to this segment are equal and opposite to these. So the taut cable means that the force in cable segment AB is tending to pull the ring from A towards B. The taut force in cable segment AC is also tending to pull the ring at A towards C. So if we pull these together, and think about what's happening at A, we have forces pulling in these two different directions, and this is what we want to focus on. To find the resultant force we're seeking, we'll need to find unit vectors pointing from A towards B and from A towards C. Note that our approach changes if the problem statement is worded differently. Suppose we had been asked what the resultant force is on the overhang. The taut cables are then exerting a tension that pulls from B towards A and from C towards A, respectively. But because we are interested in the resultant force on the ring, we want unit vectors pointing from A to B and from A to C. One other small point before we begin, you will notice that the tensile load is given in kips. This is a contraction for kilo-pound, so 1 kip equals 1,000 pounds. The three absolute position vectors in the figure are RA is 16J plus 11K feet. RB is 8I plus 27K feet. RC is 8I feet. The relative position vectors of interest are RAB, which is RB minus RA, and that's equal to 8I minus 16J plus 16K feet. And RAC, which is RC minus RA, which is 8I minus 16J minus 11K feet. The magnitudes of these relative position vectors are RAB equals the square root of 8 squared plus 16 squared plus another 16 squared, and that number turns out to be 24 feet, and the magnitude of RAC is the square root of 8 squared plus 16 squared plus 11 squared. That turns out to be 21 feet. So in this case, when we establish the unit vectors, we get some very clean fractions that come out of this. We have the unit vector from A to B is the relative position vector from A to B divided by its magnitude, and that ends up being 1/3 I minus 2/3 J plus 2/3 K. The unit vector from A to C ends up being 8/21 I minus 16/21 J minus 11/21 K. And I just noticed a small error here, so I'll go back and fix that. The resultant force at A from the two tensions is therefore resultant at the ring is equal to the tension magnitude AB on a unit vector along AB plus the tension in AC on a unit vector along AC. So that gives us 8.4 kip on the first unit vector plus 12 kip on the second unit vector and when we put all that together, we end up with a resultant that's equal to 7.37 I minus 14.74 J minus 0.686 K kips.